Thrills, spills, and a whole lot of fun. That's the world of robotic mechanical engineering, a realm where creativity meets science and imagination fuels innovation. From the tiniest of gears to the mightiest of motors, it's a universe waiting to be explored. Now let's add some equations to the mix. Consider a robot's arm lengthened by 3 times. How does that change the torque needed for specific movements? If the power supply provided to a robot is increased by 25%, what would be its impact on the robot's speed and efficiency? And if a robot's mass is doubled, how do the inertia and the force required for movement change? But wait, there's more. Suppose the radius of a robot's wheel is reduced to half of its original size. How would it affect the distance covered in one complete revolution? If a robotic arm's weight is increased by 50%, how does it change the stress on the supporting structure? Lastly, if a robot's motion sensor range is tripled, how does it influence the robot's ability to navigate through a crowded space? Keep these questions in mind as we delve deeper into the fascinating world of robotic mechanical engineering. Now imagine a robot. It's quite a complex machine, isn't it? But did you know behind all that complexity lies a simple math problem? Let's take a look at one. If a robot's motor rotates at 60 revolutions per minute, and its wheel has a circumference of 2 feet, how far does it travel in 5 minutes? It's a head-scratcher, isn't it? Or how about this one? A robot's arm needs to lift a 5-pound object. The arm is powered by a motor that produces 10 newtons of force. If 1 pound equals 4.45 newtons, can the motor lift the object? And here's a real challenge. If a robotic rover is designed to travel across Mars, and Mars has a diameter of 4,200 miles, how many wheel rotations will it take for the rover to travel from one side of Mars to the other, if each wheel rotation covers 5 feet? But robotic mechanical engineering isn't just about the numbers. It's also about the joy of creation, the thrill of innovation, and the satisfaction of solving problems. From designing robots that can explore the farthest reaches of space, to creating machines that can perform delicate medical procedures, it's a field that's all about making the impossible possible. And let's not forget, it's also about having fun. Whether it's creating a robot that can paint a masterpiece or designing a mechanical pet that can fetch a ball, there's no limit to what you can achieve with a little bit of imagination and a whole lot of engineering. So, what did we learn today? We discovered the magic of numbers, the power of creativity, and the limitless possibilities of robotic mechanical engineering. We dove into the depths of space exploration, explored the intricacies of medical advancements, and even found time for a little bit of fun and games. And remember that riddle from earlier? The answer is right there at the start, hidden in the fun and excitement of robotic mechanical engineering. So, as we journey into the world of gears and motors, remember, it's not just about the destination, it's also about the ride. So buckle up, hold on tight, and get ready for an adventure in robotic mechanical engineering that's out of this world. And as we wrap up, here's one last math problem to keep those gears turning. If a robot has 5 motors, and each motor has 3 gears, how many gears are there in total? It's a puzzle, isn't it? Well, the answer is right there in the question. Just remember, in the world of robotic mechanical engineering, the fun is always in the figuring. All right, engineers, buckle up. As we take a quick pit stop in our robotic adventure, let's shift gears and dive into some fun math problems. Remember, the joy is in the journey, and these problems are just another part of our exploration. First up, if a robot has 10 gears and each gear has 5 teeth, how many teeth are there in total? Keep that number in mind as you calculate. Next, let's move a bit. If a robot travels 5 feet in 2 seconds, how long will it take to travel 50 feet? Remember, we're looking for the time, not the speed. Now let's check our power levels. If a robot's battery lasts for 3 hours and it's been running for 2 hours and 30 minutes, how much time does it have left? Time is of the essence. All right, time for a bit of heavy lifting. If a robot weighs 20 pounds and it lifts a 5-pound object, how much weight is it carrying in total? Remember, it's not just about the weight of the object, but also the weight of the robot itself. Lastly, let's go for a spin. If a robot's wheel has a diameter of 2 inches, what is the circumference of the wheel? Remember your pi. Remember, the fun is in the figuring. Keep those gears turning and stay tuned for the answers in our next video. Until then, keep exploring the world of robotics. All right, engineers, let's dive into some more fun math problems. Remember, the joy is in the journey, and these problems are just another part of our exploration. First up, if a robot travels 100 feet and each rotation of its wheel covers 2 feet, how many rotations does the wheel make? Keep those numbers spinning as we move on. Next up, if a robot travels 10 feet in 1 second, how long will it take to travel 100 feet? Remember, we're looking for the time, not the speed. Alright, let's check our power levels again. If a robot's battery lasts for 5 hours and it's been running for 3 hours and 45 minutes, how much time does it have left? Time is of the essence indeed. Now let's talk about gears. If a robot has 7 motors and each motor has 4 gears, how many gears are there in total? Keep those numbers cranking. Lastly, let's calculate speed. If a robot travels 60 feet in 2 minutes, what is its speed in feet per second? Remember your conversions from minutes to seconds? Remember, the fun is in the figuring. Keep those gears turning, and stay tuned for the answers in our next video. Until then, keep exploring the world of robotics. Alright engineers, let's take a break from the numbers and watch some fun in action. We've been talking about the math and science behind robotics, but let's see how all that knowledge can be applied in a fun, playful context. Let's head over to a park where children are playing fetch with a robotic dog. Watch as the robot calculates the trajectory of the thrown object, adjusts its speed and direction, and fetches the object just like a real dog would. Isn't that amazing? Now, let's move into a living room where a child is teaching a robotic cat to high five. Observe how the robot recognizes the child's hand, calculates the correct height and force to apply, and executes the high five. It's not just about the high five, it's about the bond they're forming. Next, let's go to a backyard where kids are having a race with a robotic rabbit. Notice how the robot adjusts its speed to match the children's, navigates the race course, and crosses the finish line. It's not just a race, it's a lesson in navigation and speed control. Now, let's step into a classroom where a group of children are solving puzzles with a robotic parrot. See how the robot recognizes the puzzle pieces, calculates their correct positions, and helps the child place them accurately. It's not just a puzzle, it's a fun lesson in problem solving and spatial awareness. Finally, let's peek into a bedroom where a little girl is having a tea party with a robotic hamster. Watch how the robot recognizes the tea set, mimics the actions of pouring and drinking tea, and interacts with the girl and her toys. It's not just a tea party, it's a lesson in programming and sensor technology. As you can see, learning can be fun and games when you have a robotic pet. So next time you see a child playing with a pet, real or robotic, remember the science behind the fun. Let's continue our fun journey with more playful interactions with robotic pets. First, imagine a park where children are playing hide and seek with a robotic squirrel. Watch how the robot uses sensors to detect hiding places, calculate the best hiding spot based on its size and shape, and even use a bit of strategy to make the game more challenging. It's not just hide and seek, it's a practical application of sensor technology and decision-making. Now, let's take a trip to a living room where a child is teaching a robotic turtle to dance. Observe how the robot uses its sensors to detect the child's movements, calculate the rhythm and steps, and mimic the dance. It's not just a dance, it's a lesson in motion sensors and algorithmic learning. Next, we're off to a backyard where kids are having a race with a robotic horse. Notice how the robot adjusts its speed based on the children's pace, calculates the best path, and crosses the finish line. It's not just a race, it's a fun exercise in speed control and navigation. Let's then step into a classroom where a group of children are playing charades with a robotic monkey. See how the robot uses its AI to recognize the children's actions, calculate the possible words, and guess the right answer. It's not just a game of charades, it's a demonstration of artificial intelligence and pattern recognition. Finally, let's peek into a bedroom where a little boy is having a pretend dinner with a robotic dinosaur. Watch how the robot recognizes the pretend food, mimics the actions of eating, and interacts with the boy in a friendly manner. It's not just a pretend dinner, it's a hands-on lesson in object recognition and interactive programming. Remember, engineers, every moment of play is a moment of learning when you're with a robotic pet. So next time you see a child playing with a pet, real or robotic, keep in mind the science behind the fun. Let's get back to our engineering journey. After all that fun with robotic pets, you might be wondering about the nuts and bolts that make these interactions possible. Well, it's time to dive deeper into the world of robotic mechanics. First up, let's talk about actuators. Actuators are the components that allow robots to move. They're like the muscles in our bodies, enabling robots to run, dance, or play fetch. Whether it's a robotic squirrel hiding in the park or a robotic horse racing in the backyard, actuators play a crucial role in their movements. Next, we have sensors. These are the eyes and ears of robots, providing them with information about their surroundings. Sensors allow a robotic turtle to detect a child's dance movements, a robotic monkey to recognize charades, or a robotic dinosaur to interact during a pretend dinner. There's a wide variety of sensors used in robotics, including proximity sensors, light sensors, and even touch sensors, each serving a unique purpose. Finally, let's explore the concept of feedback control. This is the process that enables a robot to adjust its actions based on the information it receives from its sensors. It's like when a robotic dog adjusts its speed to fetch a thrown object, or a robotic cat calculates force to give a high five. Feedback control is a crucial component of robotics, ensuring that the robot's actions are accurate and appropriate. Remember, every step you take in learning is a step closer to becoming a great engineer. So keep those gears turning and let's continue our exciting journey in the world of robotic mechanical engineering. Welcome back, future engineers. After our deep dive into robotic mechanics, it's time to go even further. Let's explore the world of microcontrollers, power sources, and autonomous navigation in robotics. First up, microcontrollers. These are like the brains of our robotic pets, controlling their movements and interactions based on the information they receive from sensors. Whether it's a robotic dog catching a frisbee or a robotic cat giving a high five, microcontrollers play a crucial role in making these actions possible. Next, we have power sources. From batteries to solar power, the energy source for a robot determines its efficiency and performance. For example, a battery-powered robotic turtle might be perfect for indoor play, while a solar-powered robotic horse could be a great companion for outdoor adventures. Finally, let's delve into the concept of autonomous navigation. This is how our robotic pets find their way around. Using sensors and algorithms, a robotic rabbit can navigate a race course, or a robotic parrot can fly around a room. Autonomous navigation allows our robotic pets to interact with their environment in meaningful and playful ways. Remember, the journey of learning never ends, so keep those gears turning and keep exploring the world of robotics. All right, engineers, let's switch gears again. This time we're stepping out of the workshop and into the playground. You might be wondering, what do pets have to do with robotics? Well, a lot actually. Robots can be designed to mimic the behavior of pets, providing companionship and even helping children learn. Imagine a child playing fetch with a robotic dog. The robot dog could calculate the trajectory of the thrown object, adjust its speed and direction, and fetch the object just like a real dog. This would involve complex math and physics, but to the child, it's just fun and games. Picture a child teaching a robotic cat to high five. The robot would need to recognize the child's hand, calculate the correct height and force to apply, and execute the high five. Again, math and physics are at play, but the child is just engaging with a friendly robot. Now consider a robotic rabbit racing with children. The robot would need to adjust its speed to match the children's, navigate the race course, and cross the finish line. This would require complex algorithms and calculations, but to the kids, it's simply a thrilling race. Imagine a child and a robotic parrot solving a puzzle together. The robot would need to recognize the puzzle pieces, calculate their correct positions, and help the child place them accurately. This involves problem solving and spatial awareness, but to the child, it's a fun challenge. Lastly, picture a tea party with kids, their stuffed animals, and a robotic hamster. The robot would need to recognize the tea set, mimic the actions of pouring and drinking tea, and interact with the kids and their toys. This would involve programming and sensor technology, but to the kids, it's just a playful afternoon. Through these playful interactions, children can learn about robotics without even realizing it. They can see how math, physics, and problem solving come to life in their robotic pets. So the next time you see a child playing with a pet, real or robotic, remember the science behind the fun. Brace yourself, engineers, as we are about to dive into the fascinating world of robotic mechanical engineering. It's a field that combines the principles of mechanical engineering with robotics, and it's what brings those playful robotic pets to life. Firstly, let's get the basics right. Robotics is an interdisciplinary field that integrates computer science and engineering. Robots are programmable machines that can carry out a series of actions autonomously or semi-autonomously. Sounds simple, right? But there's a lot more to it. There are different types of robots, each designed to serve a specific purpose. Industrial robots, for instance, are used in manufacturing. They can do everything from painting cars to assembling electronics. Service robots, on the other hand, are used to assist humans. They can be anything from robotic pets like we discussed in the previous scene, to the robotic vacuum cleaners you might have at home. Now let's get a bit more hands-on. With a simple robotics kit, you can start building your own robot. These kits usually come with all the parts you need, along with instructions. By following these instructions and assembling the parts, you'll start to understand how different components work together to create a functioning robot. Remember, the first step to becoming a great engineer is to start learning and never stop. In the next scene, we'll continue this journey exploring more about how these amazing machines are designed and built. So stay tuned and keep those gears turning. Welcome back, future engineers. As we continue our journey into the world of robotic mechanical engineering, let's roll up our sleeves and dive into the nitty-gritty of programming a robot. In robotics, programming is the process of providing a robot with instructions that it can execute to perform a specific task. This could be as simple as moving forward a few steps, or as complex as recognizing and responding to stimuli from its environment. This brings us to the role of sensors in robotics. Sensors act as the eyes and ears of robots, enabling them to perceive their surroundings. Light sensors, for example, can detect the presence or absence of light. Temperature sensors can measure the heat level in a given area. By incorporating these sensors into your robot, you can program it to respond to changes in its environment, making it more interactive and intelligent. Now let's shift gears and talk about problem solving in robotics. Imagine you're tasked with designing a robot to clean a room. You'd need to consider a host of factors like the size and shape of the room, the type of surfaces the robot will clean, and the most efficient cleaning pattern. This is where your creativity and problem-solving skills come into play. You'll need to design a robot that can navigate the room, avoid obstacles, and clean efficiently. Remember, the only limit to what you can create is your imagination. In the next scene, we'll take a look at some real-world examples of robotic mechanical engineering, so stay tuned and keep those gears turning.